Really excited to be back again. I actually talk to you more about quantum mechanics, specifically looking at how operators are actually important in only in terms of getting observables in a particular eigenfunction, or I would say in terms of wave function, but also looking at how we're able to dive more in terms of various properties like the theorem of separability, and specifically we actually looked at, I would say, this particular expression which is called the Schrödinger's equation, where our Hermitian operator is acting on a particular wave function and producing, I would say, energies that are actually classical mechanical representations for the Hermitian operator, which is highly linked to the quantum of a particular physical quantity and reproducing our wave function in here. And this is actually, well, pretty much you guys know this to be the Schrödinger's equation in here. Now in this video we're going to dive more into special properties of operator that represents physical quantities. Now we just need, let's say, two important understandings in quantum mechanics. Now first understanding is actually where our operator is acting on a function, and this gives us eigenvalues that are classical representation of that particular operator in quantum mechanics, and this actually reproduces our function. And in here we take note specifically of A, which is called observables, and this observables is classical. Now let's move to another, I would say, understanding. The other understanding I would say is number 2, which is expectation values, and expectation values is expressed as this, and it's actually equal to the integration all space of this particular symbol, which in terms of star is called, I would say, the complex conjugate of a wave function, and this is actually included in this particular operator acting on just the wave function, and this is done tie in all space. So that being said, this is our second understanding, and this understanding here we need to take note that this here is actually called the expectation value. So once we have these two understandings, then we can compare and also play around with both of them to actually extract the Hermitian operator. So I'll be saying Hermitian operator. The Hermitian operator actually is depending on your operator specifically. So the goal of this particular video is to be able to actually move away from, I would say, operators and lean more towards actually Hermitian operators. So that being said, we're making A to become an Hermitian operator. And how can we make this capital A to be Hermitian operator? To do that, we need to make our small letter a, which is the observable, and importantly the expectation values, to be real numbers in order for this to actually exist. And this is actually expressed formulaically as this particular formula, where the integration of, I would say, a particular function, which is a conjugate complex of that particular function, I would say the function must be a well-behaved function, which is in this case f, is included in, I would say, this particular operator, which is expressed as a for now as an operator, and this operator is acting on another well-behaved function, which is g, and this is done with respect to, I would say, the partial derivative tie, which is in all space, and this is equal to the integration of now g, our operator acting on the same f, which is on the left side but now this bracket is actually covered by this complex conjugate right there, and this is also expressed in terms of tie in there, and this particular expression in here must be true in order for our Hermitian operator to actually be manifested in there and making our A to lean away from it being just an operator and become an Hermitian operator. So this A is actually the target goal in here, and this A is no more an operator, but now it's called a Hermitian operator because it satisfies this particular expression, and also it is actually producing eigen, I would say, values or observables that are in here real numbers. So in conclusion, what do we have to infer from this? What we infer in conclusion is that A in here, for it to not be an operator but rather it being an Hermitian, we need to actually introduce restrictions, and these restrictions right here that are actually applied to the operator makes it to be less of an operator and more to be an Hermitian operator, and this actually will enable us to obtain real numbers for our A, which is, I would say, the observable that is actually needed in the quantum mechanical realm of our, I would say, physical quantity. So that being said, we are actually able to link the classical mechanics and make this classical mechanics description of a particular physical quantity to actually correspond properly or better when we actually use linear Hermitian operator than just using an operator, so that we can actually really tap into the quantum mechanical expressions of that particular quantity that we're actually tackling physically. So that is about it for this particular video. Please hit a comment down below. Let me hear your thoughts about your understanding of the Hermitian operator and how it's actually different from the Hamiltonian operator, which is actually more linked to the Schrödinger's equation, but in here, which is a Hermitian operator, we're looking at how this is actually a better representation of understanding the physical quantities that are actually more in connection with the classical mechanics that is expressed as small letter a, and that's actually really tapping into the quantum mechanical explanation for those quantities behavior right there. We'll dive more into the Hermitian operator in future videos in terms of examples and things here and there. So all the same, hit a comment down below. Let me hear your thought about this. Hit like, share and subscribe, and share with your friends. Stay smart and believe in yourselves.